In the next subsection, we talk about the adjustment of the proportional action. Well, some vendors will allow you to obtain a pure proportional action by setting Ti to 0. So if you set Ti to 0 in the faceplate, what will happen is that the output of the integrator is constant. So you can see it as a bias, and you have indeed then a pure proportional action. But this is dangerous because this might give the impression that Ti small is leading to little integral action, and on the contrary, well, setting Ti different from 0 but small leads to a very aggressive controller with quite a lot of integral action. So there is kind of a discontinuity over here. It might be that when you're tuning a controller, you end up in a situation in steady state where you see an oscillation on PV resulting from an aggressive control. You would like to know if this oscillation is coming from too much proportional action or from too much integral action. Well, what you can do is look at the oscillations of MV, the manipulated value, and also the output of the controller, and the oscillations of the control error, set point minus PV, and the control error is of course the input of the controller. If the oscillations are in phase, so if you see a 0-degree phase shift, well, then the oscillations come from too much proportional action. If the oscillations of MV and E are 90 degrees out of phase, well, the oscillations come from too much integral action. Of course, in reality, you're not going to see either 0 phase shift or 90-degree phase shift. In reality, you're going to see either a small phase shift, let us say 10 degrees, and then you know that the oscillation is mainly coming from proportional action, or you might see that the oscillations are, for instance, 80 degrees out of phase, and then you know that the oscillations result from mainly too much integral action. Well, where is this magic coming from? Well, we'll first draw a block diagram of the controller. So this is the controller gain. We have the proportional part. Here we have the integral part. Right, proportional part. Here at the input we have the error. It goes through the controller gain. Here we have the proportional part and the integral part. They are in parallel, and then the two actions are added to result in the manipulated value. Right, so this is the PI controller, and let us assume we'll draw this one here in black, right, and this one here in blue, right. Well, let us assume now that we see in this first situation an oscillation on the error, and that you have here a oscillation of MV that is, well, an oscillation with a small phase shift, right? Well, this must come from the proportional action, right? Because we know that the integral action is going to introduce a phase shift of 90 degrees, right? If this comes as a surprise, you should go back in the course and look at integrating systems, right? Whereas a gain, of course, here is not going to introduce a phase shift. So here clearly you're in this situation here, too much proportional action. In the, and we might as well put a 1 over here. In the second situation, right, we have a signal that looks like this. This is the error, and what we'll have is an MV that is shifted by 90 degrees, right? And you can kind of see that this cannot come from the proportional part. The proportional part, it's again, is not going to introduce a phase shift, but of course we know that this integral part is going to introduce a 90-degree phase shift. A cosine here on the error, right, will result in a sine at the output, so a 90-degree phase shift, right? Of course, in reality, you'll have either a small phase shift, so it will mainly come from the proportional part, or a phase shift that is in the neighborhood of 90 degrees. So you can see that the oscillations are mainly coming from the integral part. So here, second case, right, it's coming from too much integral action. When tuning a PI or a PID controller, you should always look at the set point, at the process value, but very important also at the manipulated value. MV is sometimes forgotten, and even in reference books, right? There is much to be learned by observing MV. Remember this equilibrium between the proportional kick and this I ramping when tuning a PI controller for processes with delay. Also, you have to look at MV to see the saturation effects that might be present. If some of the disturbances are measured, right, or you have access to measurements that are an indication of load disturbances, well, you should monitor these signals, as they will help you explain some of the upsets that you see on the process value PV. In the next slides, I will present two systematic methods to tune a PI controller. With a bit of experience, you can also tune a PI controller in a more intuitive way by searching for an equilibrium between proportional action and integral action. You could name this method 0. For processes with little delay, the proportional kick can be higher than the steady state variation in MV, but when the ratio delay over main time constant increases, well, you will have to decrease the proportional kick. In this course, it is very difficult to transmit this intuitive approach in a few rules, so therefore I will stick to two systematic methods that you can use directly, and with time you might acquire this more intuitive way of tuning the PI controller. Well, the first method is to do first an adjustment of the proportional action, and then you do an adjustment of the integral action. So you start by optimizing a proportional controller. We'll make the assumption here that PV is on set point when you do the set point change, and that you have deactivated the integral action, and often this is done by setting Ti is equal to 0, although this might change with the vendor, the one that has implemented the PI controller. So what you do is increase the gain, the controller gain, until you obtain a closed loop response that is fast enough, right? Remember that the controller gain is used to tune the speed of response, and with an acceptable level of overshoot, right? What does that mean, acceptable level of overshoot? Well, it will depend on the type of control problem. Either you have a set point tracking problem, or you have a disturbance rejection problem, right? If you have a tracking problem, well, In some cases you might have a little bit of overshoot, in some cases you don't like to have overshoot, so it will be problem dependent. But if you're in a disturbance rejection problem, well, you're tuning the controller by doing set point changes, but you do not expect set point changes in a disturbance rejection problem, at least not very often, right? So what you can do is accept quite some overshoot, and you can use the quarter decay ratio. So if this is the set point change, right, and this is the response, we have a proportional controller, so in general PV will not be on set point, and you have a response like this, and this is the steady state value. Well, the quarter decay ratio rule is that you can go up to a value of the second peak that is a quarter of the value of the first peak. So you see that this is quite a bit of overshoot. But of course, when you have a disturbance rejection problem, you don't expect the set point to change, right? And if it does, what you can do is use the parameter b, smaller than 1 in that case, to reduce the proportional kick on MV, and it's that kick of MV that is producing this oscillation, right? If you use B smaller than 1, you count on the integral action to obtain PV is equal to set point. Once you have optimized the controller gain, what you can do is optimize the integral action, and you do this by adjusting the integral time constant. But you know from what we have seen previously that the integral time constant is of the same order of magnitude as the main time constant of the process. So you'll have to know this main time constant. You use it as an integral time constant, and from there on you can do the adjustments. Well, let us illustrate this first method, and we'll first illustrate it for set point tracking, right? So we start from a case where PV is on set point, right? Well, this is something that you can ensure by ensuring this first in manual mode, or that you have a previous controller, a PI controller that is not tuned appropriately, but that in steady state will give you a PV on set point, right? And then what you do when you're on set point, well, you deactivate the integral action. And what you can then do is do step responses on PV and look for a step response that has a good enough speed of response and that has an acceptable level of overshoot. And this will of course depend on the specifications of that you have on the system, right? And here we have chosen this response here because for this application we do not like to have overshoot. Well, once you have fixed the controller gain, and this is the response that you had with the proportional only control, you can activate again your integral action, and you can do responses with a TI that is in the neighborhood of the main time constant. And here we have a process first order with delay, so the main time constant is of course the time constant of the first order system. But in reality you will have a more complicated system, let's say a lag system, but we have seen before that you can approximate it using a first order system with delay. Well, after approximation you'll have an idea of the main time constant of the process. Well, start your optimization of TI with a TI that corresponds to the main time constant of the process, and then you can start adjusting. And you can see here that in this case, well, we'll probably choose this response over here, and indeed this corresponds with a TI, that is the main time constant of the process. And indeed this is the response, this is the controller that we have selected for setpoint tracking. Well, let's apply this method for tuning a controller in a disturbance rejection problem. So what you have to understand is that we tune the controller in the case of a setpoint change, but a setpoint change is not going to happen very often in a disturbance rejection problem, and if it does, we are going to use this trick with b smaller than 1, right, to make sure that the proportional kick is decreased or even brought to 0. So if you're tuning the controller in the case of a setpoint change, you can tune it quite aggressively to have quite a bit of overshoot, and you can even use this quarter decay ratio rules that says that the amplitude of the second peak can be up to a quarter of the amplitude of the first peak. So here we have selected this one. We could even have selected the other one, right? And now what we have to do is adjust the integral time constant, right? And what we'll do is again choose an integral time constant in the neighborhood of the main time constant of the process, so 5 seconds. If we look at the responses, well, you can select one after having tried a few candidates, and here we have selected an integral time constant of 7 seconds. This doesn't look like a brilliant performance, and you're right if you think of it as the response to a setpoint change, but do not forget that we have here a disturbance rejection problem, so setpoint changes are not to be expected very often, and if they occur, well, what you'll do is use b smaller than 1. This is the response with b is equal to 1, and this is what you do during tuning, right? But once you have tuned your controller and you implement it for disturbance rejection, you can decrease the b to make sure that the proportional kick decreases and that you have less oscillation in the case of a setpoint change. What we should do to analyze the performance of this controller is look at a disturbance rejection problem, and this is what we'll do next. In this slide we work on the same process, but we compare the controller that has been tuned for a setpoint tracking, right, and the controller that has been obtained and tuned for a disturbance rejection problem, and we compare these controllers in a closed loop situation where we have precisely a perturbation dV that looks like a step, right? So you can see the corresponding responses on PV, the responses on MV, and here we have a more aggressive controller, right? So we can, of course, this is for the disturbance rejection in light blue, so we have a proportional kick that is indeed higher. You can clearly see this. So here you have the response on PV, and you can see that, well, in the case of this tuning for disturbance rejection, PV is going to go to setpoint faster than in this other case, and this is of course because of this higher controller gain. Here we have, of course, this oscillation, but this is because we have here a step at the output. In reality, of course, a disturbance will not look like a step. It will be a much smoother disturbance. Okay, so the results that you see will be better than suggested in this simulation. The second method is the IMC PID tuning method. IMC stands for internal model control, and we will see why this PID tuning method is called the IMC tuning method. The method requires knowledge about the process, so knowledge about the structure. Is it first order with delay, second order with delay, an integrating process, and so on, and also knowledge about the associated process parameters. Often an open loop step response is used to obtain the signature and then to identify the process parameters, for instance using a graphical method. But nowadays you could also use some identification package to identify the process from any data set containing data MV and associated PV. Nevertheless, a step response is often used to obtain a signature of the system and then estimate the parameters. This open loop step response has to be done in a production environment, and you have to stay within the production tolerances, taking into account the fact that the process is non-linear, that you have noise and things like that. So the idea is to bring PV to the minimum tolerance, right? Or as close as possible to the minimum tolerance, put the controller in a manual mode and impose a delta MV that will make sure that PV is going to go close to the maximum tolerance, but of course it should not exceed this maximum tolerance, otherwise you'll have problems with production and what you're producing might be, well, worthless and will have to be thrown away. Once you have the step response, well, you have the open loop behavior of the system and you have the signature of the system, and then you can estimate the process parameters, the gain, the time constant, the delay. Either you do this using a graphical method that we have discussed before and that you have used in the laboratory associated to fundamentals of control theory, or you use some identification package. To do a step response in a production environment, you will have to convince all the people associated to production, so the operators, the process engineers, and so on, and you'll have to convince them that you are able to do a step response while not exceeding the production tolerances, right? And in this case you can see that the PV should be limited in the interval minus tolerance 40% and maximum tolerance 60%. The way to proceed is as follows. Well, in this first time region over here, you work with the PIConL, PIDConL that you have at your disposal, and this is probably a PIDConL that is not tuned well in a satisfactory fashion, right? So the idea is that you do a set point change that will bring you close to the maximum tolerance, but of course you have to use some margin, right? So some safety margin, because well there might be some overshoot in PV, and the reason why you do this set point change is because in steady state you will have the corresponding steady state value of MV, right? And this you will need when you're doing your open loop step response. Once you have settled and that you have this value of MV that corresponds to this PV below the tolerance, you do a set point change, well, to just above the minimum tolerance, and again you have this safety margin over here, and you wait until everything has settled down, right? So when everything has settled down, what you can do now is do a open loop step response. What you have to do is to go from automatic to manual mode, and then you impose a delta MV that is such that, well, your manual mode, manual value of MV is precisely the one that you had obtained previously, because you know that this value here is going to bring you to this value of PV, and this is safe, right? Because this value of PV will have this safety margin in the sense that it's, well, far off the maximum tolerance, right? And then once you have done this test, you wait until everything settles out and you have your open loop step response, right? Well, once you have your step response, you can go back to automatic mode, right? And to a controller that is running in closed loop. And this is, of course, the controller that you had previously. Then you can isolate the data from your experiment here in manual mode, your open loop step response. You have the signature of the system. Here you see that it's a first order type system with a delay, and then you can use, for instance, graphical methods to obtain the dead time, the gain of the process, and the time constant. Well, for this IMC tuning method, IMC PID tuning method, you're using a description of the process, and here it is very important to know if your algorithm, your PID control algorithm, is working with a normalized error or not. If you have a normalized implementation or not. If you do not know, well, you'll have to look at the documentation. In any case, if you have a normalized implementation of the PI algorithm, you have to use the normalized gain, right? Whereas if your control algorithm is not normalized, well, then you'll have to work with the standard gain KP. Well, the IMC PID tuning method uses the so-called desired closed loop time constant, and TCLP here, as a tuning parameter. So it's very important that you really understand what we mean by closed loop time constant and open loop time constant. Well, the open loop time constant is the main time constant of the process when you look at an open loop experiment, right? So this is an experiment where the PI or PID controller is in manual mode and you impose a delta MV, right? There is no controller active. And you look at the response of the process. And here, if we have a first order type response, you can obtain, of course, the time constant using the tangent, right, at the time of the step. This is things that we have seen before, but this is what we mean by open loop time constant. If you have several lags, what you can do is obtain the main time constant by an approximation using a Broida system, a system with a gain, a delay, and a time constant. And well, the associated time constant is then the main time constant of the system, but it's the open loop time constant of the system. Of course, you can also do a step, but in closed loop, and therefore the algorithm is active. The PI or PID algorithm is active, and therefore you have to do the step change on, here in brown, really on the set point. Here it was done on MV, right? And of course here PV, if you have integral action in your controller, should go to set point. If you're working in open loop and you do a set point change on MV, well, the gain typically will not be 1, Okay, in closed loop, of course, if your controller has integral action, the gain will be 1. And if you then look at the time constant, this is really the time constant in closed loop. And this IMC PID tuning method will use the desired closed loop time constant as a tuning parameter. And usually what you will do is take it smaller than the open loop time constant in a range that is between 0.2 times the open loop time constant up to 0.9 times the open loop time constant. Of course, this range here for the closed loop time constant is only indicative, but clearly you should not take, for instance, the closed loop time constant, the open loop time constant divided by 100, because this will then lead to a very aggressive control. Well, in this table you can find the IMC PI tuning parameters for 4 processes: first order with delay, integrating process, and integrating process with delay. In this column you have the associated parameters. So for a first order, gain, time constant; first order with delay, gain, time constant, and delay, and so on. And here you have the relevant control parameters, the controller gain and the integral time constant, right? Well, the tuning parameter that you will see in here is the desired closed loop time constant. You can see it appearing over here, over here, over here, over here, etc. Right? So this is this parameter we have been talking about in the previous slide. There is an underlying assumption, and it is that the process delay is acceptable. This means that theta is not too large with respect to the main time constant. And we will see where this hidden assumption is coming from when we look at how the IMC PID tuning parameters are obtained. In this table, well, you have to replace Kp, the standard gain, by the normalized gain if your implementation of the PI algorithm is normalized. There is another assumption here, is that we assume, and it was mentioned in the slides before but I didn't say it, right? This table is for set point tracking problems, right? So if you have a problem that is a disturbance rejection problem, what you can do is take the Kc that you see over here and increase it. Well, let us look at the 2 first model structures, first order and first order with delay. Integrating processes and integrated processes with delay will be treated later, and we'll see how we can obtain these formula later on in the course. But let's have a look and see if this makes sense. Well, you can see here that Kc is proportional to 1 over Kp. This is something that we had seen before, right? We had seen that the integral time constant was in the neighborhood of the main time constant. Well, the main time constant is the time constant for a first order system, right? And you can see here that if the delay increases in the system, well, then you have PI controllers with a decreasing gain. If theta increases here, Kc will be decreasing for the PI controller associated with this first order system with delay. So you can kind of see that these formula make sense. Another influence that I forgot to mention is that when you choose a smaller desired closed loop time constant, right, this is going to cause a more aggressive control because Kc is going to increase. You see that when TCLP the closed loop desired time constant decreases, the gain increases and the controller becomes more aggressive. Well, let us apply this second method, the IMC PI tuning method here, to a first order with delay, so a Broida model. But of course, this set of parameters could have been obtained when you have done an approximation of a lag system. So a lag system is several first order systems in series, and that you have approximated this system using a Broida system, and that the underlying model had these parameters. Well, from the IMC tuning method, if you go and look in the previous table, second line, you'll have Kc, right, is 1 over Kp. At the numerator you'll have the open loop time constant, and at the denominator you have the delay plus the desired closed loop time constant, and for the integral time constant we simply take the open loop time constant, right? So if you plug everything that is fixed in here, this is what you obtain, right? This is our design parameter. This is something that you can play with. And if you do this, and you, for instance, take a TCLP that decreases from the open loop time constant, 5 seconds, to 2 seconds, well, these are the control parameters that you obtain. And what we can now have a look at is the step responses that are associated to these PI controllers. Well, here you see the 4 closed loop responses with the set point change in brown and PV in green. You can see here that indeed when the desired closed loop time constant decreases, you have a more aggressive control, and you can see here that the rise time decreases, right? So here, depending on your specifications, you'll probably take one of these 3 responses. What I should add, of course, is also the MV that is associated to these 4 responses. Well, as promised, I have also 3 closed loop responses that kind of illustrate the effect of the parameter B, right? Remember that B comes into the proportional action, Kc proportional error, and this proportional error is B set point minus PV. This is again on our same Broida system with the same parameters, and we start from a PI controller that is tuned too aggressively for set point change, but this might actually a very good controller for disturbance rejection. The problem, as you can then see, is that if you do a set point change with the classical PI controller with B is equal to 1, you have a lot of overshoot and oscillation, right? Well, by taking B is equal to 0.5, you can see here now that you can compare the proportional kick, right? With the original controller, we had here an error of 30, right? The controller gain is 1.33, so 4/3, and you can see that the proportional kick is 40. With a parameter B of 0.5, the proportional kick has been reduced by a half, right? And we count on the integral action to bring PV on set point, and this is causing, right, less overshoot. And even if you decrease B, well, you can see that the response is still acceptable. Of course, well, the response to a set point change is now slower, right? But this controller with this B is equal to 0 or 0.5 would be a very good disturbance rejection controller and would act in an acceptable way when there is a set point change. So this B can be used, as you can see, as a trade-off parameter to make sure that a controller that has been tuned for disturbance rejection has an acceptable step response. And as you can see the effect of B on the proportional kick, right? A B is equal to 1 is a full proportional kick, and a B of 0.5 is only 50% of the proportional kick, and with B is equal to 0 it completely disappears. Well, so far we have obtained a PI controller, and remember that if we write this equation in the time domain, right, and assuming B is equal to 1, so that, well, the proportional part is acting on the standard control error, set point minus PV, we obtain Kc times the error at time t plus Kc over Ti times the integral of the error from minus infinity to the actual time, right? So you can see that this is the proportional part, and the integral part, right? And this proportional part clearly depends only on the error at the present time, right? Whereas by definition of the integral part looks at the past, from the infinitely remote past to the actual time, to the present time. So of course it kind of makes sense to add some information about the future, and we'll be able to do this by looking at the slope over here. In this slide we give some motivation for derivative action, and we compare three cases. In these three cases the set point is exactly the same, and the set point is represented by this dashed line, right? And here the three cases are really the situation that you have at this particular time instant, this particular time instant, and this particular time instant, right? And you can kind of see here that in this situation, case 1, well, PV is more or less constant in this neighborhood, it does not move, so the error is constant, so we see that the derivative of the error is 0. Here you can see that PV is increasing, right? So the error is decreasing, so the variation of the error is negative. And here you're in a situation where PV is decreasing and therefore the error is increasing, and therefore the derivative of the error is positive. If you use a PI controller in these three situations, well, you will do exactly the same thing, right? So the output of your controller will react exactly in the same fashion, right? Because you do not take into account the derivative of the error, right? And clearly you should react differently in case 2, for instance, and case 3, because in this case, well, you're going in the right direction, right? Whereas here you're going into the opposite direction, and this is really a motivation to add a third derivative term in the control equation. What we'll do now is combine derivative action and proportional action, and this yields, of course, proportional derivative action that can be implemented as follows. So here you kind of recognize the proportional action with the proportional error and the bias, right? And the parameter B that is in between 0 and 1. Remember that this B can be used to reduce or to remove, if you take B is equal to 0, the proportional kick that results from a set point change. Well, here we add the derivative action. So we take the derivative of the error into account and we multiply it by a parameter that is TD, the derivative time constant, and I'll come back to the meaning of this parameter later. But again, here we do not work with the classical control error. We use this derivative error that is defined like this. So again, we have here a parameter in front of the set point, and the difference is that usually now, well, you either choose C is equal to 0 or C is equal to 1, and the idea is again the same. If you have here a set point change in the form of a step, well, you're going to have here a derivative kick, right? And sometimes this is not desired. If it is not desired, what you do is use C is equal to 0. If you go to the Laplace domain and you set the bias to 0, this is the implementation that you obtain. And as you can see here, this is not implementable in practice, right? Because in the high frequencies, right, the noise that is on the error over here, the derivative error, and there is always high frequency noise present, will be amplified too much, right? So what we'll have to do is to add additional filtering of the derivative action to obtain a proportional derivative action that is implementable in practice. Well, remember that this input of the derivative action is the derivative error here, C times the set point minus PV, and in this case we take a binary C here. It's either 0 or 1. Well, notice that if you have a C is equal to 1, and it is typically used for systems without delay, well, then the additional kick, okay, the additional derivative kick is going to be in the same direction as the proportional kick, and the height of this derivative kick will depend on the filtering of the derivative action. We'll come back to that later. If C is equal to 0, of course, then you have the derivative action on minus PV, right? C is equal to 0, so this one disappears. And this is typically, well, done for systems with delay, right? You wait until there is a change of PV, and when the change of PV occurs, right, well, this minus here will cause in MV over here something that counteracts the P action, right? And this will allow you to use more proportional action, because you know that when the system is going to react, right, this derivative action is going to counteract this initial proportional action that you have used, right? But anyway, if you have C is equal to 1, you will typically see a peak, a positive peak. If you have a set point change that is like this, you'll have a peak like this, right? And when the system, well, then reacts finally, right, so something like this, what you will see is an action on the other side, right? Because, well, the derivative action on PV is with a minus sign, and the derivative of action on SP is with a plus sign. Derivative action only is never used. It is always used in combination with proportional action, and in most cases in combination with proportional and integral action. The derivative action is added and optimized last, so after proportional and integral action. You start with a PI controller, and if necessary, the derivative action is added. Well, derivative action is used typically for between quotes, slow processes. What is meant by that is that there is a significant second order time constant, which means that this secondary time constant is larger than 1/10 of the main time constant. It could be that you have several time constants, that you have a high order lag system. And a good example of such, between quotes, slow processes are thermal processes. Beware of unfiltered derivative action, as it amplifies the noise. We will see how you can obtain a filtered derivative action. Normally, if your PID block comes from a library that has been programmed by a vendor of control systems, there should not be a problem and the derivative action will be filtered. But I have seen cases where the block was provided by an equipment manufacturer and that the derivative action was really unfiltered, and this makes the derivative action unusable in practice. Well, let us have an interpretation of the proportional derivative action. With proportional action that we have seen first, right? So the proportional term with the bias. Well, for slow systems, and these are these systems where you have, well, several lag systems in series, it takes a while before a change in MV influences PV, right? So the controller acts at the wrong moment to correct the control error. So what we would like to use as a proportional action is something of the type where MV looks at the error but in the future. So MV is proportional to the error in the future, where TD is kind of, well, the anticipation in the future plus some bias. Of course, the future control error in T plus TD is not known at time T, right? But it is possible to construct a first order Taylor approximation of the error in T plus TD. So we can do this and we'll see a, well, graphical representation next. Well, it is the error in time T plus the derivative of the error in time T plus the, well, difference in time. Well, it's T plus TD minus T, so TD over here, right? And you can kind of see now that we have a proportional derivative action, right? So the derivative action can be seen as an anticipation, right? It allows you to kind of estimate the error in the future and take into account that, well, you have a slow, between quotes, system, and that if you use a simple proportional action, it would act at the wrong moment to correct the control error. And we will see that, well, this has a kind of stabilizing, and this is of course derivative action, has a stabilizing effect. What we have done here is an interpretation where C is equal to 1. You can see it over here, because we have the standard control error, and we have started from an interpretation where the proportional error was with B is equal to 1. But you can do similar things when C is equal to 0, but then you have to work on PV instead. So here you have this graphical representation. In blue here, the evolution of the control error as a function of time, and what you would like to do at time T is to obtain an estimate of the error in the future. Well, the actual error in the future is of course inaccessible, right? But what you can do is use slope information that you have at time T to construct an estimate of the error at time t plus td, and this estimate, as you can see, will be the error plus this component over here, right? And this component is, well, the derivative of the error at that time times td, right? And of course this will work as long as td, the derivative time constant, is not too large. Well, this is the interpretation that we have obtained previously. We want to work with the error in the future with some horizon td, right? But this value is of course inaccessible, so what you can obtain is an estimate of this error, and this estimate is based on the error at time t and on slope information at time t, right? And therefore, since the error is evolving after time t, well, of course you're only going to get an estimate. In practice, it is recommended to filter the variable, the error, because otherwise the derivative action here, the pure derivative, will amplify the noise. Remember that there is noise on the control error. This noise comes from, well, the fact that the control error is set point minus PV. PV comes from a sensor, so there will be high frequency noise on PV. And what will happen if you use this implementation, right, a pure derivative action, is that you amplify this noise, and what you'll have to do is to filter the error, and what is done is that a first order filter is used, right? And if you use a first order filter, of course, this is going to influence your estimates of the control error in the future. Well, this first order filter comes with a time constant, and what we'll do is write this time constant of this filter that will filter the derivative action as alpha constant times the derivative time constant, right? And typically this value of alpha is a value in the neighborhood of 0.1, but I consider 0.1 to be rather low, so you should probably increase this value to 0.5 or even 1 in some situations. This value of alpha is often fixed and inaccessible to the end user or difficult to access by the end user, so you should take the documentation associated with your PID controller and read it to see if you can access this parameter and how you can access it. Sometimes, well, you cannot access alpha, but you access directly the time constant of the filter. What we'll do now is look at the unit step response of a proportional derivative action. This means that we have here a unit step at the input and that we look at the evolution of MV, the manipulated value. Of course, in practice, MV will change and the process value will change, so therefore also the control error is going to change, right? But by looking at this unit step response, there is a lot to be learned. Anyway, if we have a process with a delay theta, well, at first the step response in closed loop with a proportional derivative action will look a lot like what you see over here. It is only after the delay theta that the response will start to deviate. So this part of the response will look different, right? But this part of the response will look very similar. We had this same interpretation also with the PI controller. Well, the first part of the unit step response is very easy. You have a step over here, right? And well, the output of the controller will be simply kc times this step, and this is what you see here in purple. So this is the purely proportional action. Well, for the derivative part we have to take this way, right? And the transfer function that we have to consider is kc, right? And then the derivative action will yield tds, and then we go through a first order system. So we have tfds plus 1, and we have to look at the step response, right? And luckily we have seen in section 2 that you could use the initial value theorem to obtain, well, the initial value, the value at time 0 of the step response. And if we call this one p of s here, we have limit when s tends to infinity of p of s, and this will be kc td over tfd, right? And this is indeed the peak, and this is the derivative kick. It will have amplitude kc td over tfd, and if you write tfd, the time constant here of this filter, as alpha td, this is what you obtain, right? And you can kind of see that if you choose alpha is equal to 0.1, you will have a derivative kick that is 10 times higher than the proportional kick. So alpha is 0.1 is really a bit too small. We can also look at the slope, and you will see if you go back to this section 2 that the slope at the time of the change, of this step change, is the limit of s going to infinity of s p of s minus y of 0. All right, and I will not go through all the calculations, but this yields minus kc td over tfd squared, right? You can see that the slope is indeed negative here, right? And you can see that, well, to have a decrease of kc td of tfd that corresponds to the d kick, well, this takes a time interval that corresponds to tfd. So you obtain the following interpretation. You can use tfd to kind of see how long this derivative action is going to last. If you pull and you increase tfd, well, you can see that, well, the derivative action is going to last for longer, but the peak value is going to be smaller, right? And the peak value is kind of influenced, of course, by the controller gain, by the ratio td over tfd, so 1 over alpha. Well, we had seen in the previous explanation that the filter derivative action can be implemented in the Laplace domain as follows. We had seen that the high frequency gain is indeed kc td over tfd. This is this limit when s tends to infinity, and it is this high frequency gain that causes here this d kick, derivative kick, when t is equal to 0. But you can also see that the low frequency gain obtained by replacing s by 0 is indeed 0, and this is why the steady state mv corresponding to this derivative or filter derivative action is 0. So this means that this filter derivative action is an action that is vanishing with time. For your information, you can obtain a discrete time implementation of this filter derivative action using the backward Euler approximation. What you have to do here is replace s by z minus 1 over ZTS, right? If you do this, you will obtain here a transfer function in Z, and well, you can do the inverse Z transform and obtain this relation, right, that you can implement on a PLC for the filter derivative action. This implementation is one that is liked because you can see here that the pole is TFD over TFD plus TS, so it is non-negative, right, because of course TFD is positive, and it is less than 1 for all TS. This guarantees that the difference equation is stable. Okay, the pole is less than 1 and it is positive, so the implementation will be non-oscillating. Well, you can do something very similar, and again this is for your information, and obtain the trapezoidal approximation, and there you have to replace S by 2 over TS, Z minus 1 over Z plus 1. If you replace this in this transfer function, you obtain a transfer function in Z, and by doing the inverse Z transform, you obtain this discrete time implementation, right, using here the trapezoidal approximation. Here you have the pole over here, and to make sure that it is stable and it will result in a non-oscillating response, so that the pole has to be positive, right, we need that half of the sampling period must be smaller than, well, this filter used in the filter derivative. Well, then we can complete our PI algorithm by using this line, and as you can see, we have used here the trapezoidal approximation for the filter derivative, and we have now that the output of the controller is the proportional part, the integral part, and the derivative part. This again is for your information. You have to be able to obtain the equations that implement a PI controller but not a PID controller, right? Later on in the course, we'll see how you can implement manual mode, MV saturation, interlocks, and so on. Well, we have seen that you could implement a filter derivative action by using this discrete time implementation, this recurrent equation, and program it to obtain an FB that will allow you to reproduce this filtered derivative action. Another way to proceed is to implement the filtered derivative action as follows, right? This could be done, for instance, in CFC, but it will presuppose that you have access to a block that implements an integrator, right? But you can compute that the relation from input to output is exactly that of a filter derivative action. If you have access to a first order filter, right, you can implement this relation, this transfer function of the filter derivative action as follows. Note that this implementation might come in handy if you require a derivative of a signal. This way of computing things will provide you the derivative of the signal in a robust fashion. Well, if we combine proportional part, integral part, and derivative part, this is the equation for the PIDConL algorithm that we obtain in the time domain, and we will see later that this is the parallel form in its most general form. So besides the usual parameters, controller gain, integral time constant, and derivative time constant, you have 3 additional parameters. This parameter B that comes into the proportional error, this parameter C that is a Boolean parameter that comes into the derivative error, and in this derivative part we work with the filtered derivative, and this involves an additional time constant of the filter that is used to filter this derivative action. We can also look at the implementation of this most general parallel form in the Laplace domain, and this is what you obtain, and we can go over all parameters. Right, this is the controller gain Kc, and it is used to tune or to influence the speed of response. The parameter B allows you to have a compromise between set point tracking and disturbance rejection, right? For disturbance rejection, we want to tune the controller aggressively, and if you then have a set point change, this is going to cause problems because of the proportional kick, right? And this proportional kick is going to cause oscillation and overshoot. By reducing the proportional kick using this parameter B, by taking it smaller than 1, you can find a compromise. The integral action, of course, is used to obtain a zero steady state error, and typically Ti, the integral time constant, is chosen as a value that is roughly the main time constant of the process. Here we have 3 parameters associated to derivative action. The derivative time constant allows you to work with an error that is an estimation of the error in the future, and TD here is really how much you anticipate or how far you anticipate. When you take derivative action, you have to use a filtered derivative, right? And this time constant is the time constant of the filter that is used to filter the derivative action. And you can see it also as a way of maintaining derivative action for a certain while. The ratio TD over TFD will influence the derivative kick, right? And you can also decide to do derivative action on the error. This is C is equal to 1, or derivative action on minus PV, and we have seen that this is done for different situations. This is typically done when there is no delay, and this is typically done when there is a delay. Well, let us use Simulink to look at some of the things that we've learned just before. So here we have a process with PID controller. Here we simply use the process that we have also used in the course. So time constant 5, dead time 3, and gain is equal to 1. And here we have a PID controller with all the parameters that we have considered before, right? So controller gain, bias. This is the B in the proportional error, the integral time constant, the derivative time constant, so this is TD. This is the C, right, in the derivative error, so derivative on, error, or derivative if C is equal to 0 on minus PV, and this is the alpha, right? So this will kind of define the time constant of the filter, right? Here it's alpha times the derivative time constant. We can also have a quick look on how this controller is implemented. As you can see here, you have the sum of 3 actions: proportional, integral, and derivative, and here we have the bias at the output, right? Normally you should put a bias different from 0 only if you have no integral action, although if you put something different here, the integral action will compensate for it. So here you can see that we have a derivative time constant that is 0, so we have just a PI controller, a standard PI control with B is equal to 1. So if we run the simulation, we'll have something very similar to what we have seen in the illustrations of the course. So indeed here we have the proportional kick and the I ramping and the response. Well, let us add a little bit of derivative action, right, and see what happens. And this is the response that you got now. So on top of your proportional action, you have here now a derivative kick, right? Because this derivative sees a change of set point, right? C is equal to 1. And then when the system reacts, well, you have the D kick on the other side. So here you have proportional, derivative, and then integral part that kicks in, and then the process reacts, and you have here the D kick on the other side. This is coming from the change of PV. Well, let us change the value of alpha to 0.2. So what this will do is increase the derivative kick, right? Because the derivative kick is Kc, the gain of the control, divided by alpha. And also now the time constant of the filter will be smaller, so the derivative action will be maintained for a shorter time, right? Let us have a look. And you can see here indeed that you now have a D kick that is very large, right? But you can see also that the derivative action is lasting for a shorter period. Again, when the process reacts, right? Well, you can see that the derivative action is going to produce something that is opposite to the proportional kick over here. Well, let us go back to the situation where alpha is 1, and we'll put a C at 0. So now we should not have a derivative kick when there is this set point change, and well, the derivative action is going to produce something that will counteract the proportional kick as soon as the process is going to react. So let's have a look at that. So proportional kick, integral action, and you can see over here that we have something that goes against the proportional kick as soon as the system starts to react. And this type of tuning with C is equal to 0 is suited for processes with delay as this one. Well, let us go back to the original situation. No derivative action. Have a look again at the closed loop response, and then we'll play with the parameter B, right? So here you see a proportional kick, right? The error is 10, the gain of the controller is 1, so we have a proportional kick of 10, right? Let's now take a value of B that is 0.5, right? And we should have now a smaller proportional kick. As you can see now, the proportional kick is only 5, right? The error is 10, right? But because this B is 0.5, only 50% of the set point is going to the proportional error. But we can see that due to the integral action, PV is still going to set point, right? And if we take B is equal to 0, we'll remove all, the entire proportional kick. And as you can see, this is indeed the case, right? So you count now entirely on the integral action to make sure that PV goes to set point. Well, this Simulink file is at your disposal on the web page of the course. Well, let us now look at the implementation of the PID controller in PCS7. What we'll do here is use a process that is emulated. As you can see, the system has a dead time of 2, a gain of 1, one main time constant of 10 seconds, and a secondary time constant of 5 seconds, I have removed all the noise on the simulation so that you see the undisturbed process variables. Well, before we start the tuning of the PID controller for the process that we have seen, we have to kind of understand the parameters, right, of this particular PID controller implementation, and for that we need to have a look at the documentation. And here this is quite easy. You can obtain the documentation as follows, and this is what you obtain. As I have said before, the PID control block is much more than a block with two inputs, setpoint and PV, and one output, MV, the manipulated value, and with some additional parameters. As you can see, there are many functionalities that you can play with. This is here the case for the Siemens PCS7 PID block, but it will be the same for the PID algorithm of other vendors. Of course, I will only give you a short overview without going into the details, and the idea is to make some links with this course. Well, the top part here has to do with setpoint handling, and we'll come back to that later. Well, you have ramping of the setpoint, you can set gradient limitations and things like that. So here you have the setpoint coming in, and what is coming out over here is PV, right? If you have a problem with a measurement because you're working, for instance, on a sensor, where you can use this input over here to take a simulated PV instead. Well, normally this is setpoint minus PV, and then you go through the deadband and you have, well, the error after the deadband, and you can then use limits to generate alarms, as I have shown you before. So here you have the multiplication by the gain, but you also have the possibility here to work in a normalized fashion, right? So now here we have the normalized error. You recognize over here the proportional part, the derivative part, and the integral part. Well, this parameter over here, this one, prop fac setpoint, is really the parameter B that allows you to interfere or to change this proportional kick when you have a setpoint change, right? And here you have a binary or a Boolean signal that you can use to switch on and off the proportional action. Here you have the derivative action. Here we have again a Boolean signal. This is the C from the course, right? That allows you to switch from a derivative action on the error or a derivative action on minus PV, right? And here you have the actual filtered derivative action. You recognize TD, and instead of working with alpha, we work with 1 over alpha in this block, and this is then the what they call diff gain, right? Diff gain is 1 over alpha. Here you have the integral action. Well, you see here the integrator, and as you can see here, you can switch between what comes out of the integrator and a bias that you can choose. So this is the bias from the course, this MV offset, and depending on if you have TI is equal to 0 or that you choose not to have integral action by setting this Boolean parameter here to 0, well, you will switch between the output of the integrator and, well, the offset, and what comes out here is MV. Note that this block implements the most general form of the parallel PID controller, and you can find all the functionalities that we have encountered in the course, although of course the name of the parameters is different. Note that this will not always be the case. You will find implementations that will implement a simpler form of the PID algorithm, for instance without the B parameter and without the C parameter. If we go down, we'll see that, well, here you have the output of the controller. What is added over here is the feed forward. Here you have the tracking or interlock functionality that we have encountered before. We have a limiting, and then we have also the possibility to force MV to a given value, right? And then at the output you finally have MV. Well, if you now look at the PID controller block, you will find here all the parameters that I've talked about in the explanation: the controller gain, integral time constant, and derivative constant. These are the main parameters. This is here this 1 over alpha. This prop cell, in cell, and diff cell, well, it's activation or not of proportional, integral, and derivative action. This is the parameter B, right? And this one here is this Boolean parameter that allows you to switch from, well, derivative action on the control error or derivative action on minus PV. Here you see also the deadband that we have encountered before. So you can see here that all the parameters are clearly visible, but this is because I've, well, kind of made some parameters visible, because if you take a block from the library, this same block, this is how it will look like. And as you can see, you only see here the 3 main parameters. So if you're interested in, for instance, this B parameters, well, you'll have to look at the object properties, right, and find it over here, well, in the middle of a lot of other parameters. But you can see that if you look for these parameters, in this case you will find them in the documentation, but also as an input parameter. Well, let us now come back to our process. It's 2 time constants, right? And at that time the other parts of the process are not enabled. So here we can have a look at the control parameters. Here they are. So we have a controller gain of 1. I've simply taken the gain of the process and taken the inverse, so that's 1. As an integral time constant, I've just taken the main time constant of the process, so 10 seconds. And what works very often is to take as derivative time constant, well, the secondary main time constant, and in this case this is 5 seconds. Remember that this derivative gain is this 1 over alpha, and if you set derivative gain or 1 over alpha to 2, this means that the derivative kick will be 2 times the proportional kick, right? So here we have now tuned this controller, and what we can do is do a set point change. Well, let's do a set point change of 10 degrees and go to 70. So what you can see here is the proportional kick and derivative kick. Since we have a derivative time constant of 5 and this diff gain of 2, the derivative action is maintained for 5 over 2, so 2.5 seconds, right? And well, what you can see is a bit of integral action over here, but as you can see here, well, with this tuning of the PID controller, we have a very nice response.